Hello, this is Module 14 on the development of probability. And the origins of probability are in a particular problem, the problem of the points, and we're going to talk about that today. But I don't want you to get the idea that this is the first ever problem of chance, because as far back as the ancient Egyptians, it seems like it all started there, they had things that were dice-like. They were actually made out of bones, but they were dice-like objects that they would roll and they would play games with, and they were games of chance. And of course, that continued on into the Greek and the Roman era, on down through history. But it was this game of chance, this particular game of chance, that led to a discussion between two mathematicians that resulted in the probability being developed. All right, so let's take a look at this PowerPoint on probability, and it will walk us through. Come on. And of course, the PowerPoint will be on Canvas. I mentioned before the French triumvirate. These are the three mathematicians working pretty much at the same time, overlapping in their work. Descartes and Fermat, we have already seen, work together on coordinate systems, and you can see their dates there. All three of them are French. Fermat and Pascal are the mathematicians who work together on probability, and Descartes and Pascal worked together on other aspects of mathematics, but they were certainly in touch with each other, and Descartes frequently visited Pascal's house to consult, not so much consult, but to talk about what they were working on. So here's Pascal. Blaise Pascal lived from 1623 to 1662. He died fairly early. He was only 39 years old when he died. He was born in Clermont, which again is the central part of France, a little bit to the east of where Descartes was born. He moved to Paris and spent his entire life in France. He wasn't like Descartes. Descartes moved around throughout Europe. Pascal lived his entire life in France. Born in Clermont, moved to Paris, moved back, moved back, moved back. Paris to Rouen to Clermont was pretty much the trio of cities in which he lived. He died in Paris. Early on, like so many of the other mathematicians, he showed an aptitude for mathematics, and his father was a famous mathematician at the time. Turned out his father was not of the same order of mathematics as his son, but Etienne Mathematics, the father, was pretty well known as a mathematician in his day. But he didn't want his son to only do math. So when he was young, he said, no, I'm not going to let you study math because that's all you're going to do. What I want you to do is focus instead on Latin and Greek. Well, as it turns out, Pascal continued to work on mathematics in spite of what his father said. And when he was only 12 years old, he proved completely on his own, without help from anybody else, and even without Euclid's elements, that the sum of the angles in a triangle is 180 degrees. And at that point, his father allowed him to study Euclid's elements, and he said, okay, I kind of give up. This kid is something special. And he allowed him to start attending meetings of the scholars around France. They met in Paris at the salon of Father Meurson. Marin Meurson was a priest who was also sort of an amateur mathematician, and he held these meetings of scholars on a regular basis. And these were really, really important meetings. This is where scholars would meet and they would share their ideas. They would debate the ideas. They would listen to each other. They would pose problems. They would solve problems together. And at one of these meetings, Pascal presented a paper when he was only 16 on projective geometry. And as it turned out, this paper, which introduces the mystic hexagon, was developed into the foundations of what we would call projective geometry today. Now, here's what the mystic hexagon is. If you take a hexagon, a six-sided polygon, and you inscribe it in any conic section, so that means a circle, an ellipse, a hyperbola, or a parabola, inscribe those 6 points and then draw the hexagon. Then look at opposite sides of the hexagon. Extend those sides so that the sides meet up. Well, as long as you don't have a hexagon where opposite sides are parallel, then you're going to have sides that are going to meet. And what he found out was that when you draw those hexagons, when you inscribe those into any conic section, look at the opposite sides and where they meet, you're going to get three pairs of opposite sides, 3 points of intersection. Those 3 points all lie on the same line. Pretty cool. And so you've got a couple of diagrams here that you could look at, and you can try it out. Try it out for yourself with a circle. That's the easiest one to try. Just don't draw a hexagon where opposite sides are parallel, because then obviously opposite sides are not going to meet, and that's not going to give you a mystic hexagram. So this really set the stage for Pascal as a professional mathematician in his own right. And this is when he started getting the attention of other mathematicians like Descartes and Fermat, who were a little bit older than him, who were already a part of this group who were meeting with Mersenne. Pascal was very interested in calculations, and he invented what has come to be known as maybe the first computer. It's called the Pascaline, and this machine added and subtracted just with gears and levers and all of that mechanical stuff inside it. It was about the size of a shoebox, so it's not exactly the kind of thing you could drop in your pocket and take with you to the grocery store, and it was pretty expensive to produce, so it wasn't that successful as an invention. It was successful because it worked. It did add and subtract numbers, and you can see all of these little wheels on here, and several of them still exist. So if you find a museum on computers or on calculating machines, you'll possibly find one of these early machines. He's also known for Pascal's triangle, and he introduced Pascal's triangle in this little booklet, the Treatise on the Arithmetical Triangle. That's what he called it. He didn't name him after himself. And just so you know, I think we mentioned the Pascal's triangle way back when we were talking about the ancient Chinese. This triangle has been known for years, so he didn't invent it. But what he did do was take this triangle and he applied it in several situations that made it actually useful, not just a triangle with some interesting patterns, but a triangle that could actually be used. He set his triangle up in his little booklet as a right triangle. So he's got the right angle in that top right-hand corner, top left-hand corner, and across the top row, you can see ones. If you look closely at this, you'll see the ones across the top row. You see ones down the bottom, down the left-hand column, ignoring the lines where we're counting the lines, 1, 2, 3, 4, 5, 6. So the numbers that are in the table, you've got ones going across the top, ones going down the left-hand column, and then you've got all of these other numbers that are inside there. Now, if you go down to the second row and the second column, there's a 2 there. And he said, I put the 2 there because it's the sum of the number in the cell above this one and the cell to the left of this one. So that's the rule. You fill in a new cell by adding the number above it and the number to the left of it. Okay, so keep going and that'll get it for you. Let's go over to a sheet of paper and look at how he initially used this triangle. Stop sharing and go to the document camera. So here's Pascal's triangle. And you usually see it today with a 1 on the top row, and then 1, and then 1, 1, 2, 1. So it's set up as an isosceles triangle with the ones coming down the 2 sides of the triangle, as opposed to the ones going across the top and down the left-hand side. And so on the next row, I'll fill that in because it starts with a 1 and it ends with a 1. And then 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And notice the symmetry of this. Every other row, you've got an odd number of numbers on it. So it's got a middle number, but to the left and to the right of that middle number, you've got the same numbers. It's kind of like a numerical palindrome. So the next row would be a 1 and a 1 for the first and last numbers, and then 5, 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and so on. So the first application that Pascal saw of this was in looking at how you would raise a binomial to a power. So a binomial has two terms. So a plus b is a binomial. 3x plus y is a binomial. 2z to the fourth power minus 1 is a binomial. All of those are examples of binomials. But when we talk about the binomial theorem and raising a binomial to a power, we're talking about something like a plus b to the nth power. And in this case, in Pascal's day, n is a natural number. Actually, let's say n is a whole number. Okay, so let's make a little table here. We're talking about a plus b to the 0 power, a plus b to the first power, a plus b to the second power, a plus b to the third power, a plus b to the fourth, and then I'm going to stop. Well, a plus b to the 0 power, any number raised to the 0 power is 1. A plus b to the first power, any number raised to the first power is the number itself. So this is a plus b. And I'm actually, as I go down through here, we're going to record the coefficients of every single term in this expression. So this is 1 times a and 1 times b. And when I raise a plus b to the second power, I get a squared plus b, a squared plus 2ab plus b squared. So when I write that with all of the coefficients, I've got 1 times a squared plus 2 times ab plus 1 times b squared. All right, let's stop right there. Look at the coefficients and compare them to the numbers in the triangle. On the top row, you've got a 1. A plus b to the 0 power is equal to 1. On the second row, you've got a 1 and a 1. Well, those are the coefficients of the terms when you raise a plus b to the first power. The next row, you've got a 1 and a 2 and a 1. Well, those are the coefficients that you get when you raise a plus b to the second power. So the next line, 1, 3, 3, 1, those are the coefficients that you're going to get when you raise a plus b to the third power. And when I raise it to the third power, I'm going to have, let me write the variables down first, a to the third, and then a squared times b, and then a times b squared, and then b to the third. My coefficients are 1, 3, 3, and 1. Now you might actually have that one memorized. You might actually have a plus b to the third memorized because you've used it a lot, but you probably don't have any higher powers memorized. And there are several different ways to get those coefficients. One way is to get the coefficients of a plus b to the fourth is just multiply a plus b times a plus b, get that answer, multiply it by a plus b, get that answer, multiply it by a plus b, combine all the like terms, there you go. That's going to take a while. Or use this row of the triangle to generate the coefficients because I can predict the pattern for the variables. It's the coefficients that I'm going to get when I do all of that multiplication. So this is going to have 1 times a to the fourth plus 4 times a to the third times b plus 6a squared b squared plus 4ab to the third plus 1 times b to the fourth power, and so on. Now, this was really important in future work because when Isaac Newton comes along, he is going to start this working on this binomial theorem, but he's going to expand it. So Pascal has figured, and by the way, mathematicians have been working on this for a long time. It's not like he just all of a sudden figured out how to expand a binomial. No, they've been doing this. What Pascal did was say, hey, look, this triangle is going to give you a quick and easy way to get those coefficients. And what Isaac Newton does is he says, well, that's all well and good as long as that exponent is a whole number. But what if that exponent is a fraction? What if you want the square root of a plus b? Or what if you want a plus b to the negative power, like the reciprocal of 1 over the reciprocal 1 over a plus b. Then what are you going to get? So he started here. Newton started with this and then continued the work by generalizing the value of n. Okay. All right, so let's go back over here, see what's next with Pascal. There's our triangle. And this is actually a page out of his book. So this is the print that goes along with that book, or that treatise on the arithmetical triangle that was printed in 1653. Okay, so in 1654, he and Fermat are going to start writing letters back and forth, and they're dealing with this particular problem, the problem of the points. And as they're writing back and forth with each other, they're each solving this problem in a different way. So we're going to look at the two different ways that they solved the problem. And let's come over here to the document camera to do that, to look at their two different methods. There we go. We're already at the document camera. All right, so here's the problem. You've got these people these two people are playing a game. They are equally skilled players. One is just as likely to win as the other. And they have to stop the game before it completely plays out. They started the game by each putting in a pile of money. So they each start by putting in $10. And so there's 20, somebody's going to win $20. But they have to stop the game early. So the question is, how do they divide up that $20? Does the person ahead just get all of the $20? Well, the person who's behind might say, well, no, because I'm really close, I might have caught up. Do they just divide it in half? Well, the person who's ahead says, well, that's not fair because I was ahead. So they've got to figure out a mathematical way to divide up that $20 between the players A and B. And it depends on how many more points they need to win. All right. So imagine you've got these dice or something, and they're tossing the dice, and player A and player B are playing, and each one has a 1/2 chance of winning every time you roll the dice. When you stop the game, player A only needs 2 more points to win. Player B needs 3 more points to win. So that means player A is ahead. Let me make that note. Player A is ahead in the game. Well, the first question to think about is how many more points would they play if they kept playing? How many points would guarantee a winner? All right. Well, if they play 1 more point, they don't definitely have a winner yet. Doesn't matter which one of them got it. Doesn't matter. Suppose they play 2 more points. Well, yeah, player A might get both of those, but it's not a guarantee. It's possible that player A gets one and player B gets the other one. So 2 points don't guarantee that I've got a winner. Even if I play a 3rd point, player A may have won the first one, but player B wins these next 2. Well, now they're actually tied, because now it's that next point that's going to determine the winner. So how many more points do I need? Well, I need 1 less than 2. I need 1 less than 3. And then I need that tiebreaker. If one wins 1 more point and if player A wins 1 more and player B wins 2 more, they're tied. And then they need to play a tiebreaker. All right, so how am I going to count that? How many more points would they get to guarantee a winner? A wins 1 more point and B wins 2 more points. And there's a tie. So one more point guarantees a winner. So 1 plus 2 is 3 plus that tiebreaker, that makes 4. So that makes 4 more points. Okay, 4 more points. And Fermat says, here's the way I'm going to solve it. Look at all the possibilities. If they play 4 more points. Without stopping, we're going to play 4 more points no matter what. And we're going to make a list of all those possibilities. That's exactly what Fermat did. And we even have a copy of that letter that shows his list. So when we look at those 4, how those 4 points are played out, well, player A could win all 4 of them. And I'm going to use a little a. So if player A wins all 4 of them, let's record that as A. What if player A wins 3 of them and player B wins 1? Well, maybe player A wins the first 3 and B wins the last one. Player A wins 2, B wins 1, then A wins the last one. Or maybe player B wins the second point. Or maybe player B wins the first point. Okay, there are only 4 ways that player A is going to win 3 points and player B is going to win 1 of those points. Now, what if they split? What if in the next 4 points, player A wins 2 and player B wins 2? Well, let's see what happens. Could be A, B, B, A, B, A, B, or B, A, B, or A, B, B, A, or B, A, B, A, B, B, A, and I think that's it. I've got 3 where A starts, 3 where B starts. That's it. So those are the only 6 ways that I could play the points out where player A wins 2 and player B wins 2. All right, keep going. What if player B wins 3 points and player A wins 1? Well, maybe A wins the first one and then B wins the next 3, or A wins the second one, or B wins the third one, or B wins the last point. And if B wins all 4 of them, there's only one way that could happen. Okay, so that's all the different ways to play out 16 points. There are 16 ways, to play out the 4 points. And that makes sense because for each of these points they're going to play, there are 2 possible outcomes. So 2 times 2 times 2 times 2 is 2 to the 4th, which is 16 possible outcomes. And what Fermat did was he said, well, let's go back and look at those 16 and let's see how many of those 16 did player A win. How many of the 16 combinations did player A win? Well, player A only needed 2 points. So player A wins all of these. And that's 6, 7, 8, 9, 10, 11. How many did B win? Well, he wins all the other ones. So that's 5 of them. He wins 5 of them. So I'm going to divide the stakes in a ratio of 11 to 5 in player A's favor. Another way to say that is player A gets 11/16 of the money. And player B will get 5/16 of the money. Well, they should both consider that fair. Player B should be happy because he's going away with some money. We could have said, well, the guy who's ahead gets it all. Player A should be happy because we could have said, since we didn't get to finish, let's just give everybody back the money they started with. He's still walking away with more than the $20 that he started with to begin with. Or did he put in 10? I don't remember. Okay. But this is the way that that Fermat said solve the problem. And problems similar to this, because they went on and they talked about, well, what about other problems similar to this? And Fermat's method was always grounded in, well, let's make a list. Let's make a list of all the possible outcomes and let's count them. Well, that sounds like probability, doesn't it? The definition of a probability, a favorable outcome, is that it's the number of ways that outcome can occur divided by the total number of outcomes. Okay. So don't forget that. I'm going to write that over here. Just the definition of a probability the probability of a favorable outcome is a fraction whose numerator is the number of ways the outcome can occur and the denominator is the number of possible outcomes. So it's easy to see why the probability always has to be between 0 and 1, or it has to be greater than or equal to 0 and less than or equal to 1. Okay, well, let's see how Pascal said to solve this problem. Pascal agreed with that 4 is important, but Pascal said, I'm going to use my triangle. So let me come over here and go to Pascal's triangle. And as I write these numbers down, these numbers might look familiar to you from what Fermat did. And since we're talking about 4, what did we say? 4 more points. We're going to look at this row in the triangle. 4 more points means look at this row. And the probability that person A wins, he only needs 3 more points, remember? No, I'm sorry, he needs 2 more points. And player B needs 3 more points. Well, guess what? There just happened to be 5 numbers on that row. And I'm going to divide them up 2 to 3. Remember, player A is ahead. So you don't just take the first 2 numbers and add them for A because he's going to have the higher number. He gets the sum of these first 3 numbers. Player B gets the sum of the last 2. and that's the numerator of the fraction. The denominator is the sum of all of the numbers. Which just happens to be 2 to the 4th again. And again, I get 11/16 and I get 5/16, the same thing. But going to the appropriate row of the triangle and just dividing up the numbers into the appropriate parts doesn't take nearly as long as Fermat's method. And not to mention, we've got with this triangle something that we can use on a variety of problems. For example, this works with any useful for any binomial probability problem. Shh, hush. All right, so suppose we toss. All right, so suppose we toss 5 coins. What's the probability that we get 2 heads and 3 tails? And I don't mean 2 heads in a row and then 3 tails. I mean all the different combinations of 2 heads and 3 tails. So I could do what Fermat did. I could sit down and I can make a list and just count them. But what I'm going to do is use the table. I'm going to use the correct line in Pascal's triangle to help me solve this problem. And the triangle, the line that has 5 as the second number is the right one to go to. So let me just write that down here. It's going to start with a 1, and then 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and then 1. Okay. The 1 tells you how many different ways to get all 5 heads. The 5 tells you how many ways to get 4 heads and 1 tail. The 10 would tell you how many ways to get 3 heads and 2 tails. And this 10 tells you how many ways to get 2 heads and 3 tails. This 5 tells you how many ways to get 1 head and 4 tails. And how many ways to get 5 tails is that last one. So 2 heads and 3 tails, we're talking about this one right here. So the probability would be a fraction whose numerator is 10 and whose denominator would be 2 raised to the 5th power, which is 32, which just happens to be the sum of the numbers on this row. 10 plus 10 is 20, 25, 30, 31, 32. We put 2 to the 5th, which is 10 over 32. And I'm not going to simplify that. Just leave it like that. Okay. So a binomial probability is one where you've got 2 possible outcomes, and each outcome is just as likely to occur as the other. And that's what you had in the problem of points. You've got 2 people playing. So the 2 outcomes are either player A wins or player B wins. They are equally skilled players. So the probability that either wins a point is the same. That's a binomial probability. That's what the Pascal and Fermat discussed in their letters back and forth that resulted in the foundations of probability. All right, so let's go back over here and just finish talking about Pascal for a minute. There's Fermat's method, Pascal's method. All right, one last thing about Pascal, because he is also very well known in religious studies classes or religious works. He became involved with the Jansenists in France. Remember, France at this time is a Catholic country, but not all Catholics were the same. There were different sects. And so the 2 main sects at this time were the Jansenists and the Jesuits. And Pascal becomes a Jansenist, as his whole family does. And he calls that his first conversion when he joins that group. His sister actually becomes a nun. Well, not long after that, he's active. He's always a good Catholic, but he's very active, and then for a while kind of falls out of it. Stopped being quite so active, doing other kinds of stuff. And during this period of time, he was doing a lot of mathematics, and even wrote at some point that he considered marriage, but later on said it was the lowest of the conditions of life permitted to a Christian. So good thing he never got married during any period of his life. So he's working with Fermat in 1654. They are passing letters back and forth. Their last letters between each other occur in September. In October, he has a vision. He has an accident with horses and a carriage in October where he was almost killed. And then a month later, he has a vision at night and he heard a voice. And the voice speaks to him for a very long time. And he wrote it down. He didn't talk to people about it at the time. He wrote it all down, and he carried that piece of paper with him for the rest of his life. And when he died, his family found it pinned inside his jacket. So that's how we know about it. But he said that in that vision, he heard these words, among others: fire, God of Abraham, God of Isaac, God of Jacob, not of the philosophers and the scholars. And he took that as a sign that he was supposed to stop working in mathematics. He should devote his entire life to his faith. And he did. He completely stopped working in mathematics. Now, let me tell you just a little bit before we move on. Well, during this period of time, let me move on to the next slide. During this period of time, he devotes his life entirely to his faith and his church. He continues to write, but he's not working in mathematics or science. And the document that he writes, Pensée, it's not a novel, it's not poetry, it's kind of like little essays, and it's considered a model of French literature at this period of time. So it's a very famous work, It's his own thoughts on human suffering and faith in God. And in this, he has what has become to be known as Pascal's wager. Now, this is kind of interesting because think about this for just a moment. The Jansenists were known to believe in predestination. They believed that human beings were innately evil, we were born bad, and we were only saved by God's grace. But that grace from God was only extended to a predetermined number of people, a predestined group of people. Okay. So in this document, in this book that he's writing, he talks about his own ideas about suffering and faith, but he also talks about, he's not trying to bring people from other faiths to God. He's not trying to convert Baptists or Methodists or Jews or Muslims. What he's trying to do is talk to people who don't believe in God at all. Okay, that's his audience. The skeptic is his audience. And he writes in there, if God does not exist, one will lose nothing by believing in him, while if he does exist, one will lose everything by not believing. And he uses probability and mathematical arguments to justify that belief in God is rational. So he's trying to reason with somebody who doesn't believe in God. And he's saying, using your reasoning, using logic, it makes sense to believe in God. And here's the way he explains it. Okay, first of all, across the top, either God exists or God doesn't exist. Those are the two things that could happen. Now, of course, he believes in that first column. And then he says over there in that far left-hand column, okay, so every individual has the right to choose to believe in God or not believe. And it's kind of interesting that he says we have that choice because he's from a group of people who believes in predestination, that choice has already been determined for us. So there's, a little bit of irony there. But when you look at all of those combinations, for each one of those boxes, there's a reward and there's a loss. Okay. So if God does exist and you do choose to believe in God, the reward is that you're going to gain eternal life. Your loss is that you miss out on these very brief worldly pleasures. But they are very minor, according to Pascal, they are very minor compared to that eternal life that you will enjoy. What if God doesn't exist, but you choose to believe? Well, your reward is, and this is a quote from him, you will be faithful, honest, humble, grateful, full of good works, a sincere, true friend. In other words, you're going to live a good life. You're going to be what everybody would say is a good person. The loss is that you will not enjoy noxious pleasures, glory, and good living. So he kind of makes that good living part sound like it's not as great as it could be. So what if God exists, but you choose not to believe in God? He said, this is the worst thing, because the greatest thing that you could lose is your eternal life. Your reward, this is just the opposite of the box above it. Your reward is very brief and it's very minor compared to what you're losing, that eternal life with God. But what if God doesn't exist and you choose not to believe in God? Well, your reward is brief and worldly pleasures, and you don't lose anything. If you lose nothing. So Pascal is saying to people who don't believe in God, your best bet is to operate on that top row. Because whether God exists or God doesn't exist, you're still going to live a good life. And there's the possibility that you're going to live a good eternal life. And so he tries to convince them that that's the way they should live. And so in the book, when he's talking about it, I mean, he's sort of set up a little dialogue between himself and a skeptic. And the skeptic says, but, why should I do this? I know what I'm doing. I can't choose to believe. It's just not in me to make that choice. And Pascal says, well, don't choose, just act like you believe. And if you act like you will believe, pretty soon it's going to become a habit and you're going to start to believe. Really interesting, this part of this book and his discussion of it. The way he's using, now this is during the period of time when he's not doing math, but he's using mathematical logic to make this religious argument. But then he does go back and he works on math for just a little bit longer. In 1658, he returns to some problems that he had worked on before, problems of the cycloid. And you might remember that. Imagine that you've got a point that's on the wheel of a bicycle, and as that wheel turns around and you're going to keep track of the path of that point, the bicycle's moving and the wheel is moving forward and moving around, that path is tracing out a cycloid. And one night, Pascal was in great pain, and while he was lying there in pain, he started to think about this cycloid, and all of a sudden the pain was gone. It was relieved. He saw this as a sign from God that it was okay to go back and work on this. And so he did. He went back for a very short period of time. He worked on the cycloid. He finished his work, gave it up, came back to his life, focused on his faith. And that's the way his life ended. He was only 39 when he died. During this short period of time, worked on the cycloid, volume and surface area of the solid of revolution, didn't do anything else with math. And that's why he's known as the greatest might have been in mathematics, because if he had spent all of his time pursuing mathematics, just imagine what all he might have accomplished. So a lot of our mathematicians have these little nicknames, and Pascal's is the greatest might have been in mathematics. He spent his last years in his hometown in service to the poor and attending religious services. He died when he was 39. Later on, when they did an autopsy after he died, it was revealed that he had problems with in his abdomen as well as lesions in his brain. He had tremendous migraine headaches, and it's no wonder he did with brain tumors. He's buried in this church, and inside this church is also his desk. When you go inside it and look there, you would see his desk and a little statue for Pascal. So that's it on the development of probability. We are on to module number 15 and number theory. And in number theory, we'll come back and talk about Fermat some more. See you then.